Hey everybody, welcome back to another round of physics, and yeah, let's get going. We are all at the culmination of the last 10 weeks of material regarding the magnetic and the electric fields. And I just wanted to remind you of some of the stuff that we have discussed. And in particular, thinking about the description of the electric and the magnetic field in terms of a succinct set of equations known as Maxwell's equations. Now, I should remind you of these. Two of these equations we've dealt with when we were thinking about fluxes of the electric and the magnetic field, namely the flux of the electric field through an area element is given by the amount of enclosed charge divided by epsilon naught. Okay? Now, of course, you could, the astute eagle eyes could just simply write this as phi e, is this expression here on the right-hand side. And this little circle on the integral sign is simply to remind us that we have to have a shape that is closed. In other words, there has to be a volume that is encircled by this area element. Okay. We also had one for the magnetic field. And of course, that one's slightly different because it is impossible to separate the north pole of a magnet from the south pole of a magnet. And so unlike charges, which can be easily separated, negative charges one place, positive charges to another, magnetic poles do not allow us to do that. And so regardless of how big or how small I make my enclosed volume, I will always have the same number of north poles as south poles, resulting in a net flux of 0. Okay? And again, you could think of this left-hand side as being the flux of the magnetic field through an enclosed volume, or the surface of an enclosed volume. Okay. Then we went off and, did other stuff. I guess we did this, then we went off and did circuits, then we came back and started looking at the magnetic field. And then I gave you two more important ideas. Excuse me, these are Gauss laws. Then I gave you two other important ideas. One of them relating to the change in flux of the magnetic field. And here, note that we were not dealing with enclosed volumes at that point. You could say an area element like a loop of wire. Okay? And so these are not enclosed areas. And Faraday's law told us that a changing magnetic flux, historically we'd write this as an electromotive force, but I am going to go ahead and write this slightly differently now. I will keep the negative sign. I will go ahead and leave this in terms of the flux notation. But on the right-hand side, we know that a EMF is comparable to a difference in electric potential. And I will go ahead and I'll substitute in, rather than that, we know that we can calculate differences in electric potential by a line integral. Okay? And again, this is Faraday's law. Maybe I should say that's Faraday's law. Okay. I'm being a little loosey-goosey with my negative signs. Okay. Lastly, we had Ampere's law. And Ampere's law said that we can calculate out the integral of B dot dl. And again, I need to have a closed loop of wire, for example, or a closed, I shouldn't even say loop of wire. I should have a closed path in space. Okay? And that path, dl, I'm looking at the overlap of the magnetic field with that path that I've walked around in space. And Ampere's law tells us that that overlap of the path with the magnetic field is proportional to the amount of charge encompassed or enclosed by that path. Good so far? Very good. Let's go ahead and put in the last piece. Okay? And in fact, this is why these four equations collectively together are known as Maxwell's equations, is because James Clerk Maxwell had a good insight into these equations. Okay? He looked at Faraday's law for a second and said, well, wait a minute. If a changing magnetic flux can produce an electric field, right? If a changing magnetic flux can produce an electric field, why can't a changing electric flux produce a magnetic field? Okay? Very good. Now, I'm sure that he had a lot more insight, a lot more experimentation, but I will present it as, broad brushstrokes. If a changing magnetic field can produce an electric field, why can't a changing electric field produce a magnetic field? And so Maxwell, with this profound insight, introduced what is called the Maxwell correction to Ampere's law. He said, I think that we should add another term to Ampere's law. And this is the term he decided to add. Mu naught epsilon naught d phi e dt. In other words, a changing electric flux, I think it also produces a magnetic field. Pretty cool, right? So let's first of all take a look at what Maxwell's correction does for us. Okay? So imagine, here is a setup problem for you. I said 120 nanofarad capacitor with circular plates 2 centimeters in diameter is charged by a 3.5 milliamp current at a given point in time. What is the magnitude of the magnetic field, a distance of 10 centimeters from the center of the capacitor plates? So I will try to draw the figure for you. Imagine, now we don't care about the rest of the circuit, how that current is being provided. Okay, we're given that. Okay, and so imagine for a second, I've got a parallel plate capacitor, circular plates. Here's the wire connecting one of the plates. Okay, and then I have the second plate with the wire leading away. Okay, and we are driving 35 milliamps. 35 milliamps of current onto the capacitor plate. And that's, bear in mind, that's at a brief instant in time. Okay? Now the second thing, we're given the area, basically, of the capacitor plates. It's 2 centimeters in diameter. So, of course, 1 centimeter in radius. And so we know the area of these plates is 1 centimeter squared times pi. And the question, it says, what is the magnetic field a distance of 10 centimeters from the center of the capacitor plates? So in the center here, incidentally, there's nothing there, right? It's a vacuum-filled capacitor. But we would like to know at a distance of 10 centimeters away. I'll draw it straight up here just for visual clarity. And I'll convert it to meters. So 1.1 meters away. And you could imagine, drawing a circle of radius 10 centimeters, right, centered right between those two plates. Okay. Well, let's go ahead and apply Maxwell's correction to see if we can come up with the answer. Okay. So the idea is I am looking to apply this equation in order to determine the magnetic field strength. That's an E dt. So I got to work on the right side here. So the first thing that I would like to figure out is I would like to figure out the electric field of the capacitor. Okay? Because I need to, first of all, let me find E, then I find the flux, then I find the change in E, flux. Okay. Well, first of all, E for a parallel plate capacitor. Well, fortunately for us, we already know what the magnitude of E is based on some of the previous work we've done this year. For an infinite or a very large conducting plane that is charged, the electric field is given by sigma over epsilon naught. Sigma representing, the surface charge density. So I could rewrite sigma as being the charge on the capacitor plate divided by the area of the capacitor plate. And you say, well, but Greg, I don't have the charge on the capacitor plate. I agree. Okay. Let's go a little further. We'll go a little further, okay? Let's put that on the back burner for a second. Okay. Next up, let's go ahead and figure out, now that we have an expression for E, let's go ahead and figure out what the flux of E is. Okay. And here we have to be a little bit more careful. Okay. And a little bit more careful because I'm considering this loop of 10 centimeters in diameter, but you notice that there's only a small fraction. I'll draw it in like as a purple cylinder here. You could imagine there's only a small fraction of that entire area that's experiencing a flux. So which area do I need to use? Do I use the area of the big circle, 10 centimeters in diameter, or do I only use the portion that is experiencing a flux, the one that only has a centimeter in radius, Good. Hopefully you see. I need to use the portion that is experiencing the flux. In other words, just the 2 centimeter diameter section. Okay. Now, upshot, we're ignoring fringe field effects, and the electric field is a constant value. So when I want to calculate the flux of the electric field, E dot dA n hat, which direction do you want to put n hat? Okay, we'll go that way. So we'll say that n hat is parallel to the electric field. Okay. So at the end of the day, what we get is the integral of the electric field times dA. N hat, of course, has a magnitude of 1. The electric field is being constant, and so at the end of the day, I get that the flux of the electric field is simply the Q, I'll substitute that in, Q over the area, right? And bear in mind, that's the area of the parallel plate capacitor, so let me put parallel down there, epsilon naught, times, right? The area of the parallel plate capacitor. Oh, goody, goody. Yeah, good, right? The areas cancel out. Now, the Maxwell correction, much like Faraday's law, the flux is not the important physical quantity. The change in flux is the physical quantity that we care about. And so let's go ahead. Now let us look at the change in the flux of the electric field. Okay. And here you start noticing, wait a minute, epsilon naught is a constant. So the only thing here that can change, put 1 over epsilon naught, the only thing here that can change is Q. The amount of charge that is on the capacitor plate. But wait a minute, Greg. We know dq dt as the current. So the change in the electric flux on this capacitor at this instant in time that we're looking at it is 1 over epsilon naught, I'll just say the current, I, over epsilon naught. So we've placed that expression into the Maxwell's correction. And you notice again, oh goody goody, the epsilons cancel out. And so I have something that says I mu naught is equal to the integral of the magnetic field times dl. Now, here's where we have to be just ever so slightly careful. Okay? You notice that when we were dealing with Faraday's law, we had an explicit negative sign. And we interpreted that negative sign, which we interpreted that through a rule or an idea called Lenz's law, is that if the flux increases, then nature will respond in a manner to decrease the magnetic flux. Here, I kind of think of the same thing. You notice, though, that there is no negative sign. It's a positive sign. So I'm going to think about Lenz's law, but it's almost like I do it in the opposite way. Okay? Rather than it being a negative feedback loop, I'm going to think of it as being a positive feedback loop. In other words, if the electric flux, the flux of the electric field is changing, then the magnetic field will be in a direction to enforce that change. Maybe a different way to say it is the current will run in a manner to increase that change. So thinking about that, if I say that the electric field, we said that the electric field was going to the right, and we made it parallel with n hat. So we said n hat is also going to the right. Okay? The question then is, which way would additional current need to run in order to further increase the flux of the electric field? You go, yeah. You remember side view, cutaway view. Here's my parallel plate capacitor. Current was initially running to the right. So current I is the original current running onto the capacitor plates. Because there is no negative sign, you can think of the change in electric flux will be further increased or enhanced by this magnetic field. Well, to further enhance the electric flux, I have a displacement current that also runs going to the right. Now I'll use my right-hand rule shortcut with the displacement current to figure out the direction of my magnetic field. I grab the wire with my thumb going the direction of the displacement current. I curl my fingers around, that is the direction of the magnetic field. In other words, on the top, it should be heading out at us. At the bottom, it's going into the board. And again, that's the magnetic field due to this displacement current. So now, I will just simply integrate along that same direction, out of the board at the top, into the board at the bottom. Because I am equidistant from that central wire, the magnitude of the magnetic field is constant. And so B dot dl becomes B integral of dl. Of course, if I go back, I am integrating along I chose to integrate along a circular path. The circular path because I know the magnetic field is constant at every point on that path, constant in magnitude. Okay? So I should have said that. I'm going to choose a symmetric shape. We already emphasized this. Choose shapes that make your life easier. Generally, that means dealing with symmetry somehow. So at the end of the day, this gives me, if I integrate along that path, I get 2 pi, and for lack of, I'll just call it 2 pi r. And I get I naught, mu naught. Pretty cool, huh? Let's look at this. At the end of the day, using the Maxwell correction, I get that the magnitude of a magnetic field is given by I mu naught over 2 pi r. Where have I seen that before? Yeah, that is the magnetic field produced by an infinite wire. Are you not boggled? Think about what just happened here, okay? I have this slide, okay? Imagine that you have a screen. Okay? You can't see what's behind the screen. What you do see is that you see current coming in, you see current going out. Okay? The interesting part is that it could be a capacitor plate, okay, where you have a changing electric field, okay? Or it could just be like you could model a changing electric field between two capacitor plates. You can model it as if it were a current carrying wire carrying what we call the displacement current. Now, please bear in mind, right, there is no physical charge moving from one plate to the other between these two capacitor plates. But the Maxwell correction says that we can model that situation where there's no charges moving between plates. We can model that situation as if it were an actual current. And in fact, even more so, there's a magnetic field associated with that current. And it matches exactly what we would expect for a real wire. Are you not entertained? Okay. So, I keep referencing it. Let me give you the full-blown one. Sometimes it's referred to as Ampere-Maxwell equation. Okay? Ampere-Maxwell equation. And so, in its full-blown glory, we have Ampere's law with the Maxwell correction. And this, in its final form, this is complete. Okay? That coupled with the other three equations, Gauss's law for the magnetic field, Gauss's law for the electric field, and Faraday's law, coupled with this, are a complete description of the electromagnetic fields. Okay? The electric field and the magnetic field. And you can start seeing why we refer to it as an electromagnetic field, is because changes in one produce the other. Changes in one field produce the other field. Let's hang on to that, okay? We will take advantage of that. In fact, I'm going to do a derivation next video, okay? And we will exactly emphasize that point, that changes in one will produce another field. And in fact, it's Maxwell who sat down and with his correction, he was able to show that light is an electromagnetic wave. So, hey, at that point, I say thank you for your attention. Keep up the good work. I'll see you next time.